I'm ready to go. So I shouldn't screw this up, but we'll see. Then that's usually what I say right before I screw something up. Usually the prelude to my screwing something up completely is going, I think I've really got this. I think I'm really not going to screw this up. And then, bam, I screw it up. Bam. But that's okay. That's all good. Here's the deal. I may screw it up, and you guys will rescue me from it, because we're a team, and we succeed together, and we fail together. And then we send you off to bigger and better things. That's the whole point. That's the best part. And kind of the sad part. It's a little sad. That's good. It's the important part. That's our job. Like being a parent. The goal is to make it so your kids don't need you. And they can go off and thrive and do better things. So, let's take a look here. When I say molecular weight, we know fundamentally that ionic and covalent compounds are just groups of atoms bound together. Right? We've known that since grade 9. Ionic and covalent compounds yeah, that'd be great. There's no names on them. I don't think. I didn't put names on them, did I? No. Can I ask, do you guys find the little tracking sheet, the little table of contents useful? Because if I'm wasting my time, let me know. But I found it helpful. If I'm wasting my time, please let me know. Is really a sentence that is useful all throughout. You can use that one all the time. If I'm wasting my time, just let me know. First thing I say in a job interview. Listen, if I'm wasting my time, just let me know. Do you know, I once had a job interview, and I said that to the principal, and she's like, yeah, no, we already have somebody. You probably don't want to bother coming in. I was like, thank you for letting me know. Anyway, I just on my desk. Oh, actually, if you want to throw them in the handout folder, that'd be great. Okay, so for example, I don't know, let's come up with an ionic compound, just a simple binary compound. Somebody give me a cation to work with. Magnesium it is. Somebody give me an anion to work with. Sorry? I heard oxygen, I heard sulfur. I'm going to go with oxygen this time. And what would the ratio be? Magnesium wants to give away how many electrons? Oxygen wants to take how many? Well, that's an easy one then. So in fact, somebody give me one that doesn't work as nicely. Oh gosh, I heard a bunch. There's so many. I heard nitrogen last, and I'm like a goldfish. So whatever I heard most recently gets me. So nitrogen gives away 3 electrons. Magnesium can only take 2. So we'd need 3 magnesiums to take care of 2 nitrogens, right? Okay. So what this formula actually means then is that this compound is made of 3 Mg atoms stuck to 2 N atoms, right? We know that. That's nothing new. But of course, we would call this magnesium nitrate? Nitride. Very good. Ionic or covalent? Yeah, very good. That's ionic. How do we know it's ionic? Metal and non-metal, giving and taking electrons. Yeah, can't share. Cool. On the other hand, super obvious, everyone knows what this is. That's carbon dioxide. It is covalent. And what is it? You know, like specifically, if we're counting atoms, what atoms is it made of? Yeah, 1 carbon atom and 2 oxygen atoms. I don't know why carbon gets written out and nothing else does, but whatever. You know what? Now I want to write oxygen out. You don't have to. Now, the thing of it is this. We know that the periodic table gives us the average mass of an atom of every element. The periodic table For example, what is the average mass of an atom of magnesium? $24.3050? I can't see it either. Is it 3050? Okay. And what's the unit? Yeah, AMU, which you'll also see sometimes written just with the Greek letter mu. Either or. What about carbon? What does it weigh? Is it 12.01 or 11 on there? Or 00794? 011. Okay. That's right. And that is also atomic mass units, or if you prefer, just U. Okay. So we can look at the periodic table, and we can see how much things weigh. Remind me, why did we say average? Why isn't that just what every carbon atom weighs? Why wouldn't they all be exactly the same? Yeah, what's the name for those? Good, there's different isotopes. I'm in your way, aren't I? Is that better? Great. What is different about the different isotopes? Yeah, the number of neutrons. You don't have to worry about that for this. We're just going to work with the average. We're going to assume that when we're working on a big scale, the average number will be the correct number. Does that make sense? So for the purpose of this whole unit, I don't think isotopes are going to come up once. You don't have to worry about them. So now, that means that with simple math, and like trivial math. So in my math class last session, it told me that it was condescending when I used the word trivial to describe math. So I'll try to avoid it. If I do it again, throw something at me. With simple math, we can find the mass of any molecule. All right, and so we will look then and say, for example, what is the mass of a CO2 molecule? And probably, like, I could ask you that and just say, do it. But let's walk our way through it. What does CO2 look like? Well, how many bonds does carbon want to make? This doesn't even matter, but, good practice to remind ourselves. How many bonds does carbon want to make? 4. Don't draw this yet. How many bonds does each oxygen want to make? 2, and we have 2 of them. So how does this work nicely, obviously? Yeah, double bonds, right? We'll make double bonds here and double bonds there, and we'll be good to go, right? So CO2 looks like this. Any grade 12s here? The hybridization state of carbon and CO2. sp3, sp2, sp. Very good. What will that bond angle be? Nope, that'd be sp3. That'd also be sp3. It's okay, I put you on the spot. Don't worry about it. 180. It's linear, right? One-dimensional. You're good. That was rude. That's a whole unit ago for these guys, and I just threw them on the spot. But you did great. Anyway, you guys don't need to worry about that. So, there it is. Now, what's this thing made of? Well, just like we said above, it's made of 1 carbon, and it's made of 2 oxygens. Well, then let's just do this really quickly. How much does this carbon here weigh? What's its mass? Its mass is 12.01 atomic mass units. And you'll note that we use an uppercase big M to show the mass of atoms. That's a convention for molecular weight. The molecular weight of this oxygen is how much? 15.9994. If you look on most periodic tables, it might just say 16.00. What does this one say? 15.9994, right? Yeah. Your periodic table may just say 16.00. That's fine. And what about this one here? Obviously, it's another oxygen, so it also weighs 15.9994. Nope. Cool. So that's what each part of it weighs. And by the way, in case you forget, we'll remind ourselves what that stands for. That is atomic mass units. Okay. So then how much does the whole thing weigh? Well, what would you do with them? What would you do with those masses? Yeah, absolutely. And there's probably 2 ones on that 12 if you look most places. I'm going to switch to the U notation just so you see it. So 12.011. And then to do it really pedantically, we could just write each of these out individually. Though there's probably a better way than that, don't you think? And I think Alex gave us a better way, but that's okay. We'll get to that in a second. So we add those together. And maybe you can do that in your head. I mean, that's 16 plus 16 is 32, plus 10 is 42. So that's going to be 44. And then that's going to be minus 0.0012. That's going to be plus. So that's going to be like 4.0, like 09 something. 44.009 something. And to get the exact number, of course, I'd use a calculator. 2098. See, I was almost there. I should have trusted myself. So 44.098 atomic mass units. Does that make sense? Right? If we know how much an oxygen weighs, and we know we've got 2 of them, add those together. And if we know how much carbon weighs, add that into the mix. And so if that's how much an average oxygen weighs, that's how much an average carbon weighs, then the average CO2 molecule is going to weigh 44.098 atomic mass units. How's that feel? Not too bad? Okay. Now, in my mind, I don't work with equations with this. I just add it up. Oh, golly. I just add it up. I just kind of think through, if you want, like an equation similar to, so we can say the mass of any molecule is, so again, I would never do this, but if you're a real equation guy, right, we add up all of the masses times how many of them we have, right? I don't do that. That's, who cares? Better, much better just to think of it this way. Let's look at another example. Actually, let's look at the same example. Let's just look at CO2. So to do this neatly, we'd say this. If we want to know the molar mass of CO2, we can just say, take the mass of carbon and then add the mass of oxygen. But how many of those do I have? 2. So what do I do with that number? I could add it twice, but what's a better way? Just multiply it. 2 times that. Does that make sense? Again, don't think of it as an equation. Just think of it as a logical thing. You know how much carbon weighs? Great. Plug that in here. You know how much an oxygen weighs? Great. Plug that in here. But, oh, I don't need 1 of them. I need 2 of them. Right? And then we would plug the numbers in, and we'd be good to go. We'd say mass of CO2. Again, we've already done this math, but that's okay. Is equal to 12.0011 U plus 2 times 15.9994 atomic mass units. And we're going to say that that therefore equals what we got above, which was what again? 44.098? Sorry? 2 zeros. Right. I knew that. Now note that we call covalent compounds molecules. So when I asked for that, we could call that the molecular weight. This is the molecular weight. Or formula weight of CO2. When we talk about covalent compounds, we'll only use one of those terms. If we're talking about a covalent or an ionic compound, we won't use the term molecular weight because ionic compounds aren't molecules, right? The thing about an ionic compound is there's no single discrete salt molecule. It just grows as a crystal. It's a big dumb rock, right? It just keeps growing out. Whereas water, there's individual molecules. You can actually pluck out a single water molecule, and it's not connected to the other ones. It's attracted to them. There's forces of attraction between them, but they are discrete individual molecules. Ionic compounds don't work that way. Big crystals, right? Big dumb rocks. So we'll never use the term molecular weight for an ionic compound, which brings me to example, am I on 4 now? I am on 4 now. Which brings me to example 4. What is the formula weight? Whoa. What is the formula weight of sodium hydroxide? And I want you to try that on your own. Now, I didn't give you a formula. I gave you a name. Oh. What does that harken back to? Unit 1, right? Never goes away. Never goes away. So, I need you to figure out the formula of sodium hydroxide, which is trivial. I did it again. Which is straightforward. Then, I need you to use that to figure out how much the average sodium hydroxide formula unit weighs. Are you going to throw that at me? I tell you all kinds of things. You never listen. This is the first time you listen. That's ironic, don't you think? I tell you all kinds of things. Nobody listens. I tell you to throw something at me. You're like, oh, okay. Got to do what the man says.
Progress.
Yeah. Just wait. Just doing it. Oh, about your lab. Yeah, catch me after, okay?
22.989707.
And if you want to use your periodic table, which has a few fewer decimals, you can feel free to do that. Watch the streets, well, they wasn't past. All saints be called to the morning mass, and off in the distance there rang a bell. Way off in the distance there rang a bell. And it rang for the saints and the sinners no more. Remember, this is a Sunday school. Probably.
They're just like getting the lesson and then like midway just stop.
Why should they not suffer? sung that without a capo before. That is low or high, depending on which way you want to go. Where would I usually do that? F? F is high. F is high. E flat? The people's key? E flat? That's better, I guess. All right, talk to me. What's the formula here? And this, I can't stress this back, and a few of you wanted to forget this, like on your Unit 2 test, and that's totally natural. Don't be discouraged by that, where it's like we learn something new, and so sometimes you've been conditioned by years of math classes of like, new unit, forget the old unit, right? This isn't like that. Which is like all of a sudden people start forgetting that every time you get a formula, you just got to work out what it is, right? So if a question says sodium hydroxide and it doesn't give you a formula, you're going to have to figure out the formula for sodium hydroxide. Now the good news is this one's fairly trivial. Sodium is what? Na. And how many electrons does it want to give away? 1. And then hydroxide isn't on the periodic table. Where do we find a hydroxide? It's a radical, so you'd look it up. You don't have to have it memorized. You're going to have it memorized. What's what's hydroxide? And what's its charge? -1. And I don't even need to draw a little chart here then. What's the formula of sodium hydroxide? NaOH. Right? But you do have to take that step. You gotta make sure you get the formula of it, right? So, having thusly worked out the formula of sodium hydroxide, we can now use that, excuse me, to answer this question. We want to know what is the mass, what's the formula weight of sodium hydroxide. So what did we do to do that? What did we do to do that? That's weird. Adding. All right, adding. What are we going to add together? We're going to add together, if we want to know how much a sodium stuck to an oxygen stuck to a hydrogen weighs, then we're going to take how much a sodium weighs. We're going to take how much an oxygen weighs. We're going to take how much a hydrogen weighs, and we're going to add them together. All right? And sodium, I always forget sodium. Is it 22 point something? 22 point what? Oh, so it's basically 23. Right, I should have known that. Okay. So we're going to take the mass of sodium. We're going to add to that the mass of oxygen, which you'll remember as 15.9994, and the mass of hydrogen, which depending on where you look, but usually you'll see it as 1.079. Sometimes with, what's on the end, 4? Is it 1.0794? Yes. So we can take those, and this is 22.9, what, 98? Oh, wow. Now we don't need way more decimals than we have anywhere else. Everywhere else we have four decimals on oxygen, right? So we might as well round the others to that as well. So that'd be 9897. We'll do a whole day on proper rounding, but for now, if you get it wrong, that's fine. But there's no point having one with extra decimal places because, whatever. Oxygen has 4 decimal places, so 15.9994. And hydrogen, I think it gives you 5 decimal places on that periodic table. So we'll just take it to 4, which would be 1.0079. All right, just like that. And this one actually works out to a fun number. What do we get when we add it together? Yep, that sounds good. What is it? 39.9970. And then I stuck to 4 decimals, so I'm just going to stick to 4 decimals. There we go. And the cool thing about that is that if you round it to 2 decimal places is 40.00. Sodium hydroxide is nice to work with because it's such a nice round number. Anyway, good. How did that feel? Not too bad? Which means if you could pull out a single sodium hydroxide formula, 1 sodium stuck to 1 oxygen stuck to 1 hydrogen, it would weigh 39.9970 atomic mass units. Yeah. 2 decimals there probably. Is it 1.08? Oh, 1.01? Yeah. You'll get 40.00. Yep, that's fine. Nope. So that we're going to do a whole day on that tomorrow specifically. It's a question of precision. Remember way back in the first lab you did, that density of brine lab, and we talked about the difference between accuracy and precision? Both of our answers are accuracy. I'll try that again. Both of our answers are accurate, but they differ in their precision. This is a more precise answer than that, but they're both correct. So on a test, I'm going to want you to do all your answers. I'm going to give you a periodic table on it, and I'm going to want all your answers based on that periodic table, right? I do that for assignments too, and I do it intentionally because then when people Google every answer, bless you, they get all the answers wrong. Because I want it based on the periodic, bless you again, so I want it based on the periodic table I give you. Does that make sense? Because if you look up periodic tables online, you can find ones that will give you 8 decimal places for atomic masses. But that's not what we're working with here, right? If we work with this one's kind of irritating because they don't match up. Some of them it gives you 3 decimals, some it gives you 4, some it gives you 5, and then some it rounds to the nearest whole number, but that's with good reason actually because those are unstable, so it's hard to speak of their average mass. But yeah, that was a good question. Did I answer it? Actually, are you just saying that to shut me up? Yeah, on any test or any assignment, I'll tell you which periodic table I want you to use. Which again, it's not that different tables disagree, it's that they're to different levels of precision. And we're going to start talking tomorrow. How many of you have taken physics? You guys talking about significant digits? Yes. Is he like a wicked sig figs like stickler? Because I am. So like once we get into it, like once I teach you how to round, if you do it wrong, I'm going to be vicious. The good news is it's not that hard. And we will practice a lot. But vicious, like an angry cat. Sorry? And as everyone knows, cats, godless killing machines. Very cute. Sure, yeah. Tell that to the birds. Tell that to the millions of birds who are killed by house cats every year. I guarantee your cat kills a bird. The cat's probably killing a bird right now.
Probably killing a mouse, not a bird.
No, seriously, cats kill unbelievable amounts of birds. Like in places where there's lots of house cats, bird populations plummet. That's the thing. Which, whatever, they gotta eat, I guess. Mind you, we do feed them. All right, you try one for me. We'll say, it's a very dramatic looking W. Yes, ma'am. Was it 5? Yes, it is. Sorry. What is the formula weight of, and what I used in my example, so we'll stick with it, iron 3 sulfate. Hey, that's an annoying formula to work with. Yes. This one's a little sneaky. I'm going to give you 7 minutes to work it out. All right? Don't wait for me. By the way, are you going to have to figure out the formula of iron 3 sulfate? Yes. Yes, you are. Can you do it?
Yeah.
Yes, yes, you can. Sorry? Figure it out. You're smart.
Wait, it's not just so.
Is Ruby around?
Here?
Guys, I have to photocopy something for Mr. Kelford's substitute. Whilst you do that, if somebody thinks they, if somebody thinks they have it well, why don't you come put it up? You can even take it with you if you want. You can do it at your desk. Yeah, get on it. And make sure you write the first step where you figure the formula out, right?
I need a calculator. Can I borrow your calculator?
And then exposed me, just like, actually, I'm gonna spend all time in the exam. And of course, really exactly. Super fucking lucky.
What? Let me do it.
And how are we doing? Yeah, well, it's pretty great to me.
Of course it is.
Jeez, I feel very self-conscious about my writing now. Look how nice that is. Wow. Wow. I'm abashed. Do you see how we had to first do the Unit 1 thing and just figure that formula out? Well, you're going to be doing a lot of that. It doesn't go away. Which, again, is nice, right? Because, A, that Unit 1 skill is still getting you marks in Unit 5. You know, it's going to get you marks here in Unit 3, which means we're always practicing it, which is nice, right? We get our reps in, we get our repetition. But it also means that like we're getting credit for a skill that we've learned, right? Which I like. I wish more classes kind of functioned that way, right? Like real life, where the prerequisite skills get used all the time, right? So we figured out the formula of iron 3 sulfate, and there's no shortcuts, right? We can't just be like, oh, it's iron and sulfate, right? We have to actually make the table and figure out the formula. And the formula ends up being that it takes 2 irons, giving away 3 electrons each, to properly pair up with 3 sulfates, because they only receive 2 electrons, right? Gotta do the work. Maybe you can do that in your head, in which case, great. I like to draw the little table. I like that we just basically extended the underlining of the title to make the table. That's nice. That's slick. And so then with the formula Fe2SO4, 3, we then have to, when we go to work this out, how many irons do we have? We have 2 of them. How many sulfates do we have? Well, we don't have 1 of them because each sulfate has 1, but there's 3 sulfates. So that's 3. This was done with a little bit of math wizardry, and may I humbly suggest, nothing wrong with that. My instinct would be to say we have 3 sulfurs, and how many oxygens do we have? 12. That would be my instinct. And then I'd ask you to be careful and make sure you include units. Again, I don't know what Elastruc's like in physics. I'm a real unit stickler. I do not like when we just tack them on at the end. I'm going to do math with units all the way through. So a unit goes on every number that has a unit. Because that's really going to matter. When we get going further with chemistry, the whole secret, the whole trick of the game is to keep track of your units. And if you do that, it's super easy. So we want to develop that habit early on. The last thing I'd say is, as a rule, I would always recommend showing the first step. Up to you. You don't have to. But I would always recommend, before you put the numbers in directly, and I know it feels like an added step, but you know, what is life but a series of added steps until you don't get to take any more steps? Of saying this is going to be 2 times the mass of iron plus 3 times the mass of sulfur, plus 12 times the mass of oxygen. I really like that step because it shows me that you know how to read this. Also, full disclosure, in the game of part marks, you screw this up, but you show me that first step, you're doing a lot better than if you just screw this up and don't show me that first step. But the reason I do that mark-wise is I think it's a good habit of mind. I think it's an extra bit of writing, but paper's cheap, pencils are cheap. And in the meantime, it helps us put on the paper our thinking. And this interesting thing happens. When we put our thinking on the paper, it reinforces that thinking, and we do it more often. Any questions about that? Okay. Your homework tonight is to do 10 of these online and get them right. And I want you to send them to me. I'll remind you how to get to that on the practice app in just a moment. But listen, after today, my expectation is that I can say, all right, so we're doing some chemistry and I need to know the molecular weight of calcium bromide and sodium oxide and potassium fluoride and mercury 2 oxide. And I need you to just know that. Does that make sense? Which means this skill needs to be ingrained. And if a skill is going to become ingrained, it's not enough to understand it. You have to have it pass from understanding into that entirely different portion of the brain, skill, right? Understanding something is one thing, but the skill to do it is an entirely different thing. And interestingly, you can have one without the other. There are math things that I did not understand until I was a math teacher. But boy, I could do them because I'd had them drilled into me in 1,000 math worksheets. You know what I mean? And on the other hand, there are things I understand that I'm not really all that comfortable doing. You know, I understand fully. I did it with my dad a couple times, how to pull the engine out of a car and replace the head gaskets. Ask me how well I would do if I had to do that on my own. Not well. You know, I just don't have the skill. I don't have the muscle memory and that sense of how to do it. So I need you to make sure that this passes from thing that we've talked about, thing that hopefully you understand, into thing you can do. And the way you do that is by practice. How do you get to Carnegie Hall? Practice, practice, practice. That's how. So chemistry practice, if you go there, one of the options should be molecular weight. Really, it should say formula weight, because actually this is all ionic crap. So I should change that title, but that's okay. And give yourself a challenge, right? Go there. And for the first few, have it give you the formula. That's cool. Here's one we could do together. Rubidium fluoride, RBF, right? Okay, well, and by the way, do this with a piece of paper. Write the questions down. You know what I mean? Like, just because it's on the computer doesn't mean you shouldn't use a pencil and paper, because that's going to be the best way to learn, right? Probably you don't want to do this in your head. And so I would, oh, for God's sake. Okay. So I would look and say, okay, the molar mass of rubidium fluoride is going to be sorry, I shouldn't use the term molar mass yet. You guys don't know that. The molecular weight of the formula weight of rubidium fluoride is just going to be the formula weight of a rubidium atom plus the formula weight of a fluorine atom, right? And then we could just look at the periodic table. From the periodic table, how much does a rubidium weigh? How much? 85 point what? 4678? Great. What's the unit on that? Yeah, you can put atomic mass units if you like. And what about fluorine? I should know this one. Is it 19? 18 point? 8800 kind of thing? So after that's a 4? Cool. All right, we'll stop there, because then they agree at 4 decimals. 840. Okay, so that's a 4. 4. Okay, and obviously 85 plus 19 would be 95. 94, so that's going to be 94.46. Oh gosh, 62. Oh, right. There's a 10 there. 104.4662, right? Yeah, cool. Can't ignore that second digit, or that first digit rather. Cool. All right, there we go. And so we put that in here. By the way, because this is using a different periodic table than you, it has a habit of saying you're wrong because you're wrong in like the 5th decimal place. Don't stress about that, okay? So I need you to be smarter than my program is. It tries its best to match you in rounding, but if it says you're wrong and it's just because your last digits don't match, that's more than likely just because you're working with different periodic tables. Does that make sense? You can still count that as correct. So look at me. If it says you're wrong, but you're wrong like in like the 3rd or 4th digit of the decimal place, you're not wrong. You're fine. You're good. You're just working from different periodic tables. If it says you're wrong and we had said 111 point something, then you're wrong. Does that make sense? But I tried to make it have a little bit of a fudge factor so it can tell if you're just working from a different periodic table. But my coding skills are, shall we say, finite. And then again, here you can say show history. And there it is, right? And what I want you to do is keep going until you get 10 correct. Again, I don't care if it says that you got 10 correct. 10 where you're with, you're at least to 2 decimal places, get the same number. I'm a happy boy. Does that make sense? Cool. Send that to me, which you can do here by clicking send your results to Mr. O. Yeah, go nuts. Computers are here. And again, work on paper. Don't cheat the system, all right? You will learn more working on paper. Don't cheat the system. It won't help you. You will do yourself a favor by learning to do this for real, and the way you learn to do it for real is by doing it. All right? There's no substitute. If I could wave my little jazz hands up here and make you know how to do this, I would wave my little jazz hands up here and make you know how to do this. But guess what? I can't. So you just got to practice. All right? Bon chance. Now you want your question answered, I suppose. Sorry? Yeah, you bet.